Bueno, es un placer introducir a Yannick Guedes Bonthonneau, que es el autor del mejor artículo de la revista de la UMA en los años 2020-2021. El jurado lo integramos con Alicia Dickinson, Marco Salvay, Nora Viviane y yo. Así que bueno, fue un trabajo arduo revisar los artículos. Y realmente este artículo nos impactó. Y bueno, fue por unanimidad la elección del tema. Entonces les quiero contar un poquito del artículo antes de presentarlo. Este artículo estudia un tópico natural e interesante sobre el que prácticamente nada debe haber sido hecho. Los campos vectoriales de Anosov juegan un importante papel en geometría y sistemas dinámicos. Varios autores construyeron espacios anisotrópicos de distribuciones para estudiar propiedades espectrales de dinámicas hiperbólicas, de las cuales los campos de Anosov son un buen ejemplo. En este trabajo, el autor estudia campos vectoriales sobre una variedad compacta cerca de un campo vectorial de Anosov. Bueno, él nos va a contar los detalles técnicos. Entonces, el nombre del artículo es Perturbation of Rule Resonance and for Storm Anisotropic Space. Bueno, ahora lo hizo más corto, Perturbation of Rule Resonance. Yannick Bonthonneau, adelante. You can start. Okay.
Muchas gracias. Quería empezar diciendo que fue un placer escribir ese artículo y también un placer publicarlo en la revista de la UMA. Estoy muy honrado por recibir ese premio, pero voy a hablar inglés porque si continuar hablando español no va a ser español, va a ser portuñol. Entonces es mejor que hable inglés mismo. So I'm going to talk about my paper and I'm going to present the result, but before I have to maybe introduce a little bit what's the context. So in my talk, M will be a compact manifold, X will be a vector field, and it's a smooth vector field with associated flow phi-t. And when I write phi-t, I think of the flow, and when I write exponential of tx, I think of the action of x on functions, because x being a vector field differentiates functions. Okay, so I have two notations for the same thing. Then I'm going to say that x is an Anosov, which is a very standard definition by now, if the tangent space of M decomposes as a neutral direction, E0, which is just the direction of the flow, then an unstable direction and a stable direction. Okay, and this is a vector bundle decomposition. So implicitly, I'm assuming that X is vanishing nowhere. And my unstable and stable bundle are characterized by the following fact. So I have some constants such that for all time positive, the differential of the flow in the stable direction is decaying exponentially fast. And for all negative times, in the unstable direction, differential of the flow is also decaying exponentially fast. Okay, so these Anosov flows are a very standard object in dynamics, and the most well-known example is the geodesic flow of hyperbolic surfaces. In some sense, the very notion of Anosov flows was invented to generalize the dynamical behavior of these flows. Okay, and the fact that the geodesic flows of hyperbolic surfaces have an interesting dynamical behavior is a very old observation. At least it's at least a century old observation. And the notion of Anosov flows is only 50 or 60 years old. Now, and also flows are also a particular case of hyperbolic dynamics. And the word hyperbolic here and here, well, it's not, you know, completely related. I don't know. And I'm not going to talk a little more about hyperbolic dynamics because that would lead me too far. Okay. And so these are very important examples in dynamics, and many questions have arisen during the years over these objects. And I'm particularly interested in one particular kind of question, which is related to the famous theorem of Blanc, Keller, and Liverani of 2002. Okay, and it's the following thing. So define for real part of S large enough the resolvent of the vector field, which is just the Laplace transform of the flow. Okay, so you take a function, you compose it by the flow, you put an exponentially decaying weight, and then you integrate all of this, okay, and say you are acting on continuous functions, okay. So for a real part of S large enough, this operator converges, okay, and it's a honest bounded operator on continuous functions. Now, obviously, if the real part of S becomes not so large, then at some point the integral will stop to converge, and it's not clear a priori that you can define the resolvent of X. So this here so far is not the theorem. The theorem is the fact that if X is an author, this map can be continued to C as a meromorphic family of operators that take smooth functions and map them to distributions. So originally, my operator was inputting continuous functions and outputting also continuous functions. But if you want to continue in the complex plane further, then you have to allow that your operator will lose a lot of derivatives, and that it does not preserve continuous functions or L2 functions or any classical functional space that you can learn in a bachelor. Okay, so this is a very important theorem for many reasons, and it leads to a natural definition, which is the following. So the poles of the resolvent are called resonances, and more specifically, Polycode-Ruel resonances. I will just say resonances in the rest of my talk so that it takes less time. But and then I will also explain why, because this is a theorem of Blanc, Keller, and Liverani, and why the name is Polycode-Ruel. So these poles are called resonances, and the range of the residue. So this is a family of operators. So the poles have residues which are operators, and these operators are projectors. And the range of them are called resonance states. So these resonances provide us with a discrete spectral set for X. And I mean, this is it's a very good news because a priori a vector field. Imagine that you have a vector field which is that preserves the volume. Okay, so if you make this, you see this vector field as an operator, unbounded, acting on square integrable functions. Then the spectrum of this operator is just the imaginary line. And in terms of spectral theory, having continuous spectrum, usually you don't know. I mean, it's a harder kind of situation. And if you have discrete spectrum, you have a lot more tools to do a lot more of analysis. So for a spectral theorist, this is a very good news. Okay. So I said that this was an important theorem, and I want to explain now, I guess, the biggest success that was related to this theory of polycode-Ruel resonances. And it's related to a famous paper. The famous paper is 1967. And in this very long paper, among other things, he defines the following zeta function related to X, and it's an infinite product over periodic primitive trajectories. Okay, so periodic orbits, and primitive means that you just go around once, and you take the product of 1 minus exponential minus s length of the orbit, and just take all of this inverse. So if you remember the Riemann zeta function, this mimics the zeta function because recall that it has also an infinite product presentation. So you product over all the primes, 1 over 1 minus p to the minus s, okay? And so here, p is replaced by exponential of the length of the orbits, okay? And so Smales defined this product and observed that it converges for real part of S large enough. And the question that that pops up is the following: does zeta x continue to a larger set? And recall that originally Anosov flows are a generalization of hyperbolic flows of geodesic flows of hyperbolic surfaces. And in the case, the specific case of geodesic flows of hyperbolic surfaces, this zeta x is a function that you can relate to the Zerberg zeta function. So it's related to eigenvalues of the Laplacian on the surface. And it's been known for a long time that those functions actually are meromorphic on C, okay? So the question does not come from nowhere, okay? But still, famously, Smale writes just after asking the question that it would be quite surprising that this is true. And this is 1967, right? So then Ruel and Polycott independently in the 80s prove that yes, indeed, it continues to a larger set. Okay, so here I can be a little bit more precise. It converges for a real part of S larger than the topological entropy, and so it continues to real part of S larger than the topological entropy minus epsilon. So in this work from the 80s, Ruel and Polycott are able to prove that you can continue in a small strip to the left of the half plane where the product converges, okay? And this is already a very strong statement because the topological entropy is a pole, and once you've continued the function past the first pole, you can use a lot of methods from complex analysis to study the number of periodic orbits. So, for example, you know, you have the prime number theorem that tells you how how many primes are smaller than big N when N grows. And this is related to taking the zeta function and doing some complex analysis with the first pole. Well, here the same thing happens. And so you can count and give very precise estimates on the number of orbits with length less than N when N grows from these results, okay? So historically, that was quite important. But it's a much less strong statement than the next one, which is Giulietti, Liverani, Policot, and this is 2013, okay, so it's much later, and it depends profoundly on Blanc, Keller, and Liverani's paper, at least the theory behind it, and the answer is that yes, for S in C. Okay, so instead of a small strip, now you can continue to the whole plane, okay? And you also have a description of the zeros and the poles. So the zeros and the poles are related to the resonances for X acting on differential forms. So far, I only talked about X as a vector field differentiating functions, right? But you can also make X act on differential forms using the Lie derivative. And then you can define also resonances, and Blanc-Keller and Liverani's paper theorem actually applies, to differential forms and Lie derivatives. Okay, and so that's the reason why these resonances are called polycode real resonances, because the first ones who actually obtained poles of a continuation of something were Ruel and Polycott in the 80s. Now the question is not completely over yet, because actually Smale in his paper defined axiom A flows, and then he asked his question about axiom A flows, which Another flows are a particular case of. So then we have a paper of Dyatlov and Guillermo, and this is 2018, if I'm not mistaken. And the answer is yes, for also axiom A flows. Okay, and this is the final answer to Smale's original question. And you can see that this is 51 years after Smale asked his question. So it was a very long-standing problem that was finally solved 4 years ago. Okay, so I think that's the most striking application, I guess, or at least the one that's easiest to explain. Now, following this kind of results, there's a second line of investigation, which are topological results. And so what are those? Basically, relating resonances and resonance states at zero with topological information. For example, I give you a manifold, and I give you an vector field on this manifold, and I ask you from the resonance states and the fact that zero is or isn't a resonance for some Lie derivative action, can you tell me some topological information about the manifold? So how many connected components? What's the Euler characteristic? Can you give me the cohomology of this manifold, and this kind of information? So it turns out that it works quite well. Okay. For example, there's a Dang and Rivière, and I think it's 2017 paper, and they proved that so if you look at the resonance states S equals 0, and you take the differential. So here I'm working with differential forms. This is quasi-isomorphic to the Durham complex. So if you compute cohomology with resonance states, well, you recover the usual cohomology of your manifold. Okay. Now there's another result, which is again Dong, Guillermo, again Rivière, Chen. I think it's 2017 also. They solve Fried's conjecture in 3 dimensions. And Fried's conjecture is something that's relating zeta x of 0 with some topological invariant called the torsion. Okay, and it's not exactly zeta x, because zeta x is one particular zeta function. You have to replace it by some other zeta function. I'm not going to enter in more detail than this about this theorem, because it would take me 50 minutes just to define both sides of this arrow. But in any case, an important step in the proof is to look at a perturbation. Look at a map like this. So you have a family of vector fields x tau. All of them are Nosov. Then you can compute some value, some specific value of your zeta function for these Nosov vector fields, and then you differentiate. And you want to know that you can actually, differentiate, and then you can compute the result. So for topological kind of results, you need to know that you can do perturbation theory. Okay, and that's where my paper comes in. Okay. And before I change, I go to another part of my talk. I just want to say that these are two fields of questions relating resonances, but there are many more questions that you can ask about these things that have been quite successful. Okay, so okay. So before I explain exactly what happens for this perturbation theory, I have to explain the philosophy of Blanc-Keller and Liverani's theorem and how, what the whole theory stands on. Okay, and so how are resonances built? And the big idea, and this is an idea that was missing in Ruel and Pollicott's papers, so it's something that people did not know how to do in the 80s, and they did not know how to do them in the 90s, and they only started to be able to do it at the start of the 21st century. So the big idea is to build sequences of spaces Bn satisfying three assumptions. So the first assumption is that smooth functions are embedded in your Banach space, and the Banach space itself is embedded in distributions, and all those embeddings are continuous and have dense image. This is just a condition saying that these Banach spaces are Banach spaces of distributions, and they are not, abstract spaces. Okay, so they are related to distributions. But this is not specific about the vector field. The second condition is that x minus s as an unbounded operator acting on Bn is Fredholm for real part of S larger than minus n. And the last condition is that the propagator of x is a strongly continuous semigroup. Okay, and if you know something about the Freedom analytic theorem, you will deduce two things. Is that the spectrum of X intersected with real part of S larger than minus n is discrete. So that's just by virtue of being Fredholm, and this strongly continuous property implies that the spectrum is discrete. Okay, so it's discrete and does not depend on Bn. What I mean by does not depend on Bn means that if I find another family of B prime n satisfying the same assumptions, then I will get the same spectrum. Okay, and when you study PDEs, or I don't know, yeah, usually PDEs, you're accustomed to having many different spaces. So you have L2 spaces, continuous functions, L2, LP, Bezos spaces, and all kinds of constructions. But it turns out that you cannot use directly those classical spaces to study X and find resonances. You have to build custom-made spaces to actually be able to do something, to say something about the spectrum. Okay, so you have to really build them. That's the point. And the second thing is that, as you remember in the theorem, I was saying that it continues as a family of operators that take smooth functions and map out distributions. But you may know that the space of operators from smooth functions to distributions is a very wide space, and it's very hard to do functional analysis on such a space. So doing analysis, what is happening here? Okay. Doing analysis on operators from a Banach space to itself is much simpler, and that's why we have to build those sequences of spaces. Okay. So so far, I'm not saying anything about how do you actually build the spaces, right? But it already took some time for the people to understand that that was what was needed. Okay. Now, so the heuristics are the following: the BNs should be anisotropic. And what this means is that U is in Bn should mean, okay, two things, is that U is smooth along stable leaves and U is irregular along unstable leaves. So I have an unsoft flows, I have stable and stable distributions, which are subbundles of the tangent space, but they can be integrated into stable and unstable foliations. So these spaces should be anisotropic, but the problem is that the foliations are holder, they're not smooth foliations. And so it's really hard to actually build a space that, satisfies these heuristics. So to understand that this was the kind of space that you needed is something I think people understood in the 90s already. But to be able to actually provide such a space took at least 10 years. And it's a continuous improvement. I mean, people improve the constructions over the years. Okay. So there are many different constructions, and as I said, the end result does not depend on the space. So if you can cook up some kind of construction and it works, then go for it and do your thing. But still, there are two main families of spaces. And so the first one, and it's related to Blankeller and Liverani's construction. It's a construction by hand. Okay, so you have your product structure. So say this is a stable manifold, this is unstable manifolds, and then you look at cone, you use the fact that your Nosov flow is cone hyperbolic, and then you have some cones, well, in the stable direction, and you want to, how can I say this? Differentiate in the directions of the stable cones, and you want to integrate in the direction of the unstable cones, and you take L1 norms on some sleeves, and then you take a soup and you differentiate, and you actually build something by hand. So maybe it would look like something like this. So you take some submanifolds, a set of submanifolds, you take a soup over the elements of this set, then you take CK functions on this submanifold, and you differentiate something like this, and this would be norm of U. Okay, so I'm taking a family of submanifolds, and on each of them I integrate U against phi. So phi is CK, so this is allowing U to be C minus K, to have to be a distribution of order K, and then I differentiated this with respect to X. So for example, here the F would be directing along the unstable direction, and I would be differentiating in all directions. So as you see, this is a very hands-on construction, and you have an interplay of functional analysis and dynamics at every step of your construction, okay? Okay. Now the second type of spaces, which we can call microlocal spaces, is the kind of space that I'm specialized in. So I will probably try to convince you that they are better. And if someone else comes and is from the other school, they will probably try to do the contrary. So it's good for me that I'm the one talking today. And these microlocal spaces, they appeared in Fa.E.A and Jostrand's paper in 2011, and they always take the form following. So Bn is an up of exponential Ng times L2 of M, and here L2 of M is the usual space of square integrable functions. This up, it's a usual quantization procedure, and if you don't do microlocal analysis, you probably don't know what's a quantization. But I hope that you believe me if I tell you that it's something that you can take off the shelf, and it's a classical object in microlocal analysis that you do not have to invent to study this problem, and you do not have to adapt. It's not related to your vector field. It's just something that already exists, just as the L2 of M is not particularly related to the action of your vector field. Okay. Now, at some point, the vector field has to come in, and the only thing that you have to adapt to your vector field is this G function, which I call an escape function. And formally, it's a smooth function on the cotangent space of M. Okay. So right at the start, you see that all the functional analysis in this construction is contained in this L2 space, okay, which is a very standard functional space. And then this quantization procedure that takes a smooth function on the cotangent space and gives me an operator. And this is functional analysis, right? But it's a piece of functional analysis that is not related to the flow, and is completely independent. So what's good with these spaces is that you separate the dynamics and the dynamical analysis from functional analytic arguments that you have to deal on their own. So now I wrote that this is a function on the cotangent space, and it's not clear for someone who does not study macroelectrical analysis why I should be on the cotangent space of my manifold. So it's a general principle of macroelectrical analysis that so macroelectrical analysis is just a study of functions that oscillate very fast, okay? And when you want to measure oscillations, and I mean, if you want to study regularity of functions, if you use the Fourier transform, in principle, there's an interplay between regularity and oscillation. So functions that are very irregular, formally, you can decompose them as sums of functions that oscillate very fast, right? So studying regularity and studying oscillations is closely related. Anyway, when you study oscillations and very high oscillations, the natural place to measure those things is the cotangent space. Okay, so that's why the cotangent space pops up here. And there is a lot of interesting features in the cotangent space. And the first one, the most important one of them, is that the cotangent space is a symplectic manifold. Okay, and now X was a vector field on M, and I can lift it to a Hamilton vector field HP. The Hamilton vector field of P, and P is a function on the cotangent space. It's a Hamiltonian, and it's just the following thing. It's just psi of X. So you take a covector psi at point X and just let it eat the vector field. Okay, I had my flow phi t, and when it's lifted to the cotangent space, it just becomes let's give it a name, capital Phi of X psi is just phi t of X, and the differential of phi t minus transpose applied to psi. And so here you see that I was studying phi t, and my new flow, where it keeps the information of phi t, and it also emphasizes on the differential of my flow. And this will tell me, how orbits separate. But when you compose by the flow, this will tell me how the flow changes regularity of functions. Okay. Okay, and now oops, no, I don't want that. Okay. Recall that I had three conditions on my spaces. The first one was that smooth functions are embedded in Bn, and Bn is embedded in distributions. The second one was a Fredholm condition. The third one was a strongly continuous condition. So now I can translate those conditions in terms of my function g. So the first one is more or less equivalent to saying that g is infinity and has nice asymptotics as psi goes to infinity. So the original manifold M is compact, but now I work on the cotangent space, and the cotangent space is a vector bundle. So in each fiber, you can go to infinity in the fiber direction, okay? And you have to say something about how G behaves when you go to infinity in this way. The second condition, which was that X is supposed to be Fredholm, you can translate it as saying that HP of G is less than -1 when psi is large enough and P of psi is 0. Okay, and so this is a dynamical condition, okay, and it's saying that along the orbits of the flow, my escape function decreases. And the third condition is that globally, HP of n is bounded above. HP of G is bounded above. Okay, and now IP equals 0 is for all covectors. You need that HP of G is bounded above. Okay. So these are my three conditions. And now all the difficulty is actually building a function G that satisfies these assumptions. Okay. Now let's come back to perturbation theory. Okay. The theorem, so there's an informal version of the theorem, is that resonances depend smoothly on smooth parameters. Okay. Before I write a formal statement, you have to recall, and I'm sure you've all made this exercise at some point in your life. If you study matrices, n by n matrices, finite size matrices, and you want to understand how the eigenvalues of your matrices vary when the matrices vary, you know that if the eigenvalues are all simple, then they depend smoothly on the matrix. But then if two eigenvalues collide, some algebraic singularity could happen. Okay, and that's the case of, say, if you assume that the matrix is all the matrices are all diagonalizable. Okay, if you allow nilpotent matrices, maybe it's even a bit more complicated. But basically, eigenvalues of finite size matrices it's an algebraic problem, right? It's very, very smooth, and still in that case, eigenvalues do not depend exactly smoothly on the matrix. You always have to allow for some algebraic singularity at some places. Okay, so when I write here that resonances depend smoothly on smooth parameters, I will put some brackets here because I mean it in the same sense as eigenvalues of finite size matrices. Okay, if eigenvalues collide, some things will happen that will not be smooth. Okay, so maybe I will try to write a formal statement. So let tau gives x tau be a smooth family of unausert vector fields. Let lambda 1, lambda n, u1, un be resonances with their resonance states counted with multiplicity. Oops. For x naught, so here tau tau is a real number living in a small interval around 0. Okay, and I just take a finite number of resonances for x naught. Then there exist maps that take tau and gave me lambda j of tau, uj of tau, defined for tau small enough. Maybe I have to take tau much smaller than epsilon, okay? They are continuous and smooth when lambda j is not equal to lambda k. Okay, so that lambda j of tau, uj of tau is a resonance state for x tau. Okay, so it takes some space to just write the statement. So I had to, these maps are continuous, but when two resonances intersect, then you have this algebraic singularity phenomenon that I talked about just before. So you cannot ask that these lambda j's are actually smooth for all values of tau, but you can ask that they are smooth when eigenvalues do not collide. Okay, so that's the first point. The second point is that it would be possible that when tau moves around, the resonance just goes to infinity, because these resonances they live in a complex plane, and my operators are not self-adjoint, so I don't know that this spectrum is a spectrum of real numbers. It's actually really a spectrum of complex numbers. And when you vary the parameters, it's completely possible that just the resonance go away. And so that's why it's always defined for small parameters. Okay, maybe I can. It's possible, Okay, so just drawing a picture. It's possible that for x naught you have a resonance here, and then it moves around. And it just escapes in finite time when you move around the parameter, and at the same time, another one comes in from infinity. Okay, so it can be a bit wild. Okay, and that's the best thing that you can say about those objects. Okay, so that's the theorem in my paper, and just observation. So for lambda 1 equals 0 and functions, in the case of functions, so when you act on functions, 0 is always a resonance. Okay, so you can perturb all you want. 0, the resonance at 0 will not move. Okay. But the resonance states, they can move. Okay, so for lambda equals 0, for the resonance at 0, what's interesting is perturbing the resonance states. This was already known. Okay, and actually, I'm not quite sure, but I think, let me just check. Yeah, Bertollet, Livrani. Okay, so it was already known in 2007, I guess. Okay, but the statement for the general thing, it was not known before. I guess was not a surprise, but it was not known. So an observation is that even though it was already known, it was known using the first type of spaces. And so I said before that the second type of spaces, it's one of the interests is that you can separate the functional analysis from the dynamical analysis, you know, and so technically some things are easier. But there's also one thing is that if you want to study wavefront sets, which is an object in microlocal analysis, the second type of spaces is much more adapted, okay? And so if you want to perturb, and when you're doing your perturbation, you want to study also the perturbation of the wavefront set, then it's not really useful to know that you can perturb the resonances using the first type of spaces, because the first type of spaces, they do not give you a lot of information about wavefront sets. And wavefront sets are useful when you want to for example, in the topological kind of questions, you want to, so the resonance states are actually currents on your manifold, and you want to take products of these things with other currents, okay? And to be able to do this, you need to know that some wavefront set condition is satisfied. And so you need to have information about the wavefront sets of your resonance states, okay? So that's why, even though the fact that you can perturb the eigenvalue at 0 was already known, it was not known with the same kind of spaces. So this is still, even for that case, my result is it could be useful. Okay. And so basically, I don't know who among you has already tried to perturb a spectrum, but there's a big theory about perturbing spectra, and it's a Cato theory. And if you read Cato's books, it's a very, very long book with very hard conditions, very complicated analysis. And the end result is that if you have a family of operators acting all of them on the same space, then you can perturb things. And if you have families of operators that do not act on the same spaces, then your life is hell. You will not be able to do anything unless you do very complicated analysis that is basically trying to come back to having a fixed space. So when you want to perturb your resonances, the only thing that you really have to do is to find one space which is good for all the vector fields. So what you have to do is that you have to build those Banach spaces that I talked about before, so that they are suitable for each x tau in your small window. Okay. Yes. Okay. So in the first type of spaces, remember, I didn't explain in much detail, I didn't explain in any detail how their construction works, but the way an Ossoff property comes in the construction is that you use the fact that these flows are cone hyperbolic. So you have systems of cones that are contracted by the dynamics or expanded. And it's a very well-known fact, an easy fact, that being cone hyperbolic is stable under a small perturbation. So if you take your x naught, it's cone hyperbolic for some system of cones. You build your space using only those cones. If you perturb x naught to some x1 which is close enough, x1 is still cone hyperbolic for the same cones, and the same space will also be suitable for x1. So this is a bit schematic, okay? But basically, saying that the first type of spaces, it's almost built in the space that you can do perturbation, okay? For the second type, well, it's not obvious. And you can actually build a Forge-Armstrong, a macro-local space with an escape function G that is not suitable for perturbation. Okay, it's an additional condition on your function G that you can perturb, and that if G is suitable for x naught, then it's suitable for small perturbations. One has to build a specific G for this, and that's the thing the technical thing that I had to do in my papers. And once you, it's not particularly difficult. You just have to understand that that was what you had to do. Okay. I think that's all I wanted to say today. I don't know how much time I've been talking here, but probably too long. And again, I want to thank you for inviting me to give a talk. I would have been delighted to come to Argentina. I've never been to Argentina, but I just had a baby, and so it made things a bit difficult for me. But I hope in the future it can be possible.
Okay, thank you. Thank you very much for your talk. Are there any questions, preguntas? No questions? Okay. Thank you for choosing our journal for publish this very nice article. We thank Yannick again.
Thank you.
Okay. Thank you, Yannick.
Thank you so much.
Well, thank you.
Thank you.